In this video, we're going to do our first example problem using conservation of mechanical energy. Conservation of mechanical energy says that if we have a process where only conservative forces act, then the change in kinetic energy during that process plus the change in potential energy during that process is equal to zero. In other words, the combination of kinetic and potential energy is a constant. For this problem, we're going to be using the gravitational potential energy. So remember that when we use the gravitational potential energy, we set a zero level. Any object which is at the zero level has a gravitational potential energy of zero. An object which is a height h above the zero level has a gravitational potential energy equal to the mass of the object times the free fall acceleration, then times the height h above the zero level. And here we have our usual formula for kinetic energy, 1/2 the mass times the speed squared. When we do this problem, we're going to be using the procedure 5 handout for mechanical energy. This handout is available at the module introduction. Anyways, in this problem, we have a cliff here, and then down at ground level, we have a cannonball launched from a cannon. The cannonball has an initial speed, which is known. So then it gets launched at that initial speed, goes up, and then comes down. And then right before the cannonball hits the cliff, it has a speed v final, and we are trying to find that final speed. Okay, let's look at what the handout has to say. So step 1 says draw diagrams illustrating the initial and final situations. So we can use this diagram. This would be our initial situation here where the cannonball is fired. And this would be our final situation here right before the cannonball lands. 1b says set the zero level for gravitational potential energy. Usually I like to set the zero level for gravitational potential energy at the lowest point in the problem, not always. But in this problem, we'll just set the zero level here at that base level from which the cannonball is fired. That way we start with a gravitational potential energy of zero, and having a zero in there tends to make things simpler. Okay, now we go to step 2. We have option A and option B. Option A applies if all forces acting are conservative. So the only force acting in this process is the gravitational force. As we've seen in the earlier videos, the gravitational force is conservative. So let's see what option A tells us to do. Okay, so if all forces are conservative, we want to calculate PEG, that's gravitational potential energy, PES, that's spring potential energy, and KE, kinetic energy, for both initial and final situations. Now, I haven't introduced you to the spring potential energy yet, but fortunately, there's no springs in this problem. So we're just going to work out expressions for gravitational potential energy and kinetic energy in the initial and final situations and not worry about the spring potential energy in this problem. Okay, so here's what we do. We want an expression for the initial kinetic energy. We want an expression for the initial gravitational potential energy. Then at the final situation, we want an expression for the final kinetic energy. And we want an expression for the final gravitational potential energy. So why don't you pause the video here, see if you can fill these 4 things out, and then once you've given it a shot, you can rejoin the video. All right, so initial kinetic energy, we're just going to use the formula for kinetic energy. So I'm going to put in 1/2 mass times the initial speed squared. The cannonball is fired from the zero level. An object at the zero level has a gravitational potential energy of 0. Final kinetic energy, use this formula again, except we're going to put in 1/2 mass final speed squared. And then final gravitational potential energy, we use the formula here. In the final situation, the mass is a height h above the zero level, so we're going to put in mgh. So that was step 2 on the handout. Now let's go to step 3. Again, we have option A if all forces are conservative, option B if non-conservative forces act. The only force acting here is the gravitational force, which is conservative. So let's go to step 3. Step 3 has the equation for conservation of mechanical energy written in 2 different forms. Now, you can use either form. My preference is this lower form that has the deltas in it. It says change in gravitational potential plus change in spring potential plus change in kinetic energy equals 0. Now, in this problem, there is no springs. So we're going to take this equation, just ignoring the term for spring potential energy, and write change in gravitational potential energy plus change in kinetic energy is equal to 0. Okay, the change in anything is the final value minus the initial value. So change in gravitational potential energy would be gravitational potential energy final minus gravitational potential energy initial. Change in kinetic energy would be kinetic energy final minus kinetic energy initial. So that would be equal to 0. So what do we do now? Well, we have our equation for conservation of mechanical energy. We're going to take this stuff up here, substitute it in, and solve the problem. Okay, let's make our substitutions. Final gravitational potential energy is mgh. Initial gravitational potential energy is 0. Final kinetic energy, 1/2 mass times final speed squared, minus initial kinetic energy, 1/2 mass times initial speed squared. All that sums to 0. Notice that each of these terms has the mass in it, so we can divide through by the mass, so the m's go away. And now it is just a couple algebra steps to isolate the v final. So how about we take these other 2 terms and move them to the right where the signs are going to switch. So I then get v final squared over 2 equals, all right, take this to the other side. I get v initial squared over 2. Take this to the other side. I get minus gh. I have, let me squeeze in one more step here. So I'm going to multiply through by 2. That gives me v final squared equals v initial squared minus 2 gh. Okay, now taking the square root of both sides, I have final speed equals the square root of initial speed squared minus 2gh square root. Let's do the substitutions now. The initial 65 meters per second, and we square that, minus 2. G is 9.8 meters per second squared. H, 210 meters. Square root the whole thing. Now, putting all that into my calculator, I get 10. And as far as the unit, notice that this term has units of meters squared over second squared. This term also has units of meters squared over second squared. And actually, I get 10.4 carrying to the third significant digit. Anyways, the unit comes out to be meters per second, as we would expect for a velocity. And now we have done our first example problem using conservation of mechanical energy.